So, over here is a list of things that we might be interested in mounting. And here are things that we use to mount them with. First of all, keys. What do? They help us transmit torque. Pins. They help with torque and axial. Set screws, we don't know exactly what those do. Interference fit is very tricky, but both. And retaining rings are great for axial location stuff, and splines are great for torque. All right, and we'll talk about those in a little bit. Here's just another picture from a different book of a typical gear reducer. This is a worm gear reducer, and we can say that in reality the shaft has all sorts of shoulders going on here, right? So let's start here. Well, it looks like there's this is actually, it looks like maybe a some sort of a collar here, maybe. This, oh no, this is actually the hub of the gear. And then here is a shoulder right here for this bearing. Right, so that's what that is. And it looks like this bearing also might have a little step in it. And so here's another, or this might be some sort of adjustment. So adjustment shoulder there. And then there's another bearing here. And that bearing looks like it matches that bearing too. And so there's a shoulder in the shaft there. So lots of stuff going on. The shaft is much trickier than it looks, right? So again, we have to consider the layout of the components, the supporting axial loads, and providing for the torque transmission, right? So typically we'll do that with a key that sits down in here. Let's just draw that there's maybe a key down in there. And assembly and disassembly. This is a big one, right? Every semester, someone says, "Well, I've got a shaft and I've got a gear. I'm just going to use two shoulders," and then they draw their shaft like this, and then they draw their shaft like this, and then they say, "I'm going to wonder if I can get a different color ink here." No, I can't. Oh well. And then they put their gear that kind of sits down in like this. Right, so this has their gear in it like that. And this is great. It certainly would not go anywhere. But how do I assemble this? Right, I mean, there's no way to get that in there. So you really have to please pay attention to how you're going to assemble and disassemble this thing if necessary. Right, and that's where like a compress or an interference fit or a press fit is not so good for disassembly. All right, how do we transmit torque? There's a number of different ways to do it. We are going to stick with the square key for your project. So we'll talk about that in some detail. But there's other types of keys. So the square key, here's the full width of it. But because it's square, it's also got the width here. I would call that width and height, right? But since it's square, it's width and width. There's what's called a flat key. And typically the width is 1/4 of the diameter, right? And so the height is half of what the width is, right? And so, or the height is 3/4 of the width, right? So it's not quite half; it's about 3/4. Another really common one is round, and this will get pounded into place. Here's a gib key, right? That's really easy to slide into place because you can kind of drop it in the slot and then that slides over like this. You could screw the key into place. There could be two keys like this. If you are much of an auto type of mechanic taking apart transmissions, there's a lot of these rounded keys called Woodruff keys. They go in and out really easily. Or if you work in the machine shop, a lot of the mills and lathes are powered with Woodruff keys. They're very precise, very easy to take in and out. So a bunch of different types of keys. All right. How does this thing get loaded? All right. Well, if it's a loosely fitted key and it's allowed to wiggle in there, then it's going to get, if if the hub is trying to go this way, the shaft is trying to go this way, it's going to get cockeyed and there's going to be a real point load there, right? So point load's generally bad. If it's tightly fitted and we have the same relative thing, it won't be allowed to tip over. However, it'll be loaded in compression here, loaded in compression here. And if we have compression down low and compression up high, then we also see that there could be shear here. So we have compression there, sigma compression, and then same thing over here, there. And then here we have tau, right? That way. And keep in mind that typically key is about 1/4 of the diameter, right? Okay, so those are the kind of how the key sits in there and how the key works, right? And remember that key goes in and out of the page some. So actually, wait, before we talk about that, let's, I've got a key here. And yeah, so here's my key. Give ourselves a little bit more light. And so obviously this is made out of balsa, but say it goes on the shaft and it would go like this. Well, how does this thing get loaded up? Let's say this hand is the hub and the hub is trying to go this way, so that there's a big load here trying to push it like this. And then on the opposite side, this is amazingly hard to do, by the way. This pushes here, right? So we have the width and the height are the same. The width and the height are the same. And it gets loaded on this face over here, okay? So let's try to figure some stuff out here. We'll go like this. Okay, so maximum torques, all right? The first thing we have to think about is, what's the maximum torque of our shaft? Well, we know that the torsional shear stress is, 16 times the torque over pi d cubed. My stylus is actually being very well behaved here. This is great. And so if I sub the shear strength in here, let's see, SSY for tau, and I solve this thing, then I would get, let's see, I want to solve for the torque. So torque equals, that stays there. The pi d cubed goes over here, so it'll become SSY times pi d cubed. And I'm left with just a 16 on the bottom, I think, right? Yeah, okay, so that's good. So that's the maximum. That deserves a dotted box, I think. So that's the maximum torque. This is obviously with a safety factor of 1, based on the shear strength, the yield shear strength of the material. Now, what about the key? All right. Well, the key is really transmitting torque. So let's look up here again. Yeah, so it's getting pushed here and pushed here in compression. So what is this area here? Let's take a look. So I'm pushing on here, right? So I've got the full, it's the height, the full height. No, it's not. It's only half the height, right? Only half the height here, but then the full length. So I got half the height, the full length. So it's this face here that's going to be the compression. Oh, I got to go back onto, so I'm trying to be clever here. Okay, so the key in compression, well, let's just do a little torque calculation up here on the side. So I know that torque equals, well, it's the force on the key times the radius, which is actually d over 2. Right? And then for the square key, I know that the width and the height are the same. I'm going to address those later on. All right, so if I'm looking at the compressive load on there, I know that the sigma, right, sigma compressive, is going to be the force, right, which is, I'm going to relate to the torque in a little bit, divided by, what is it? It's the height of the key times the length of the key divided by 2, right? Because it's only half that area, just the top half. So I can rewrite that as sigma equals 2f over the height of my key and the length of my key, right? So now I can say that, let's see, the force, if I solve this again for the force here, so let's go down here. So force will equal, let's think about this. So I'll replace, this time I'm just going to replace the regular yield strength. And then I got an HL that comes to the top, and I divide that by 2, right? Yeah, there's a 2 there. So that's the force, and then so finally my maximum torque will be the force times the distance over 2. So I'm going to take this, and then I'm going to take this, and then so that means my torque will be the force, which is the yield strength, HLD divided by 4. All right, so that's the maximum torque that that the key can carry, right? And it's this is the yield strength, of course, of the key. So yield strength of the key, right? Because if that yields and it squashes over, then we're going to have problems, right? But now let's take a look at it in shear. All right, so here again, we've got this key, and I've got some, like maybe this thing's trying to go like this, and this thing's trying to go like this. Well, just so you can see it better, let's say this is going this way, and this is going this way. So it's being loaded in shear, but really the plane that's getting sheared is this plane, right? So it's actually right in here. This is the plane that's getting sheared, the center line. So it's the force, right, divided by this area. Right, so let's take a look at that. So I know it's the same old force. So tau is that force, but this time I'm just dividing it by the whole width times the length. Right, that's what's getting sheared. So I don't really have, and then I can just solve for the force and swap that out. So F equals the shear strength, right? Because this is a shear, right? Shear, and then times W times L, right? And once again, I'm going to take this guy again and sub it back in here down the same way. So my torque equals the shear strength, Sy times the width times the length times the diameter, and all that gets divided by, oh, just the 2 there. Oh, that's interesting. Okay. So I see that failing in compression, I divide the torque is only this yield strength divided by 4, but for this thing to fail in shear, it has to be divided by 2 only, right? So it seems like, oh yeah, it's going to fail in compression every time. This is the weaker thing here. But wait, right? Look at this. This is the yield shear strength, and this is the just tensile or compressive yield strength. Are those related? Yeah, they are. Right? How are they related? Okay. If you believe the maximum shear stress failure theory, right? If we believe that, in other words, if you believe the data, which apparently recently not everybody does, but I know that in compression, let's write that over again. The maximum torque equals Sy times HLD divided by 4, and then in shear, it's the torque equals SSY times the, well, width and height are the same thing, so it's H times L times D 2, right? And remember that I can do this because H equals W, right? Well, so if I believe that if I do the Mohr circle method, the maximum shear stress method, um, under no, not maximum shear stress. Oh, no. You know what? This is the problem. Yeah. Under MSS, this is exactly 1/2, right? So torque equals SSY, which is SY over 2 HLD over 2, right? Which really equals SYHLD over 4, right? So that's the story here. But under distortion energy theory, right, if you believe that, then torque equals the shear strength is actually 0.577-ish or 0.58 SY times HLD over 2, right? And 0.5 over 2 is a little bit more than a fourth, right? Which means that this key is actually a little bit stronger than, in the shear than in compression, which means that T max under compression is just a little bit less than T max due to shear, right? So the result of this is that I can always kind of, and we know that this matches the data better. I made my joke a little too early. So this matches the data a little bit better. And so I know that the compressive, my key is likely to fail in compression before it fails in shear. All right. And so let's keep going here. Oh, yeah. This is important, especially for your project. Where's my thing here? Important for project. Right. These are very standard key sizes, right? Keys come in for a square key. It comes in 3/32, 3/32, 1/8, 1/8, 3/16, 3/16. And then the keyway depth is, of course, 1/2 of the height, right? And it kind of gives you a range like this. I guess the point of this is just to show that these keys come in very standard sizes, and so by quotes stock metric key that's kind of redundant, right? By stock metric key stock. Key stock is the metal. Stock is stuff that comes off the shelf, right? For project. And I'll provide you with a better table for standard key stock. Alternatively, if you just look it up in McMaster-Carr, you'll find that they have key stock, just standard key stock. All right. Okay, now what's next? Oh, yeah. So if the key is in there, let's go back and look at this. Right, there's one little detail here that I kind of skipped, is this detail here. That, oh yeah, there's this this groove that this thing sits in, right? That's called the keyway. And so we can't really use a key unless we have a keyway. And there's a couple different ways that those are manufactured. One is that there's kind of like this fly cutter or key. I think there's a name for this. So if you work in the shop, I don't know, tell me what it is. But there's this tool here that just kind of gouges out this keyway, right? And this is called a sled runner keyway because it's kind of, sloped up at one end. It could be maybe the snowboard keyway or something like that, freestyle ski, where it's tipped up at both ends. Alternatively, there's this kind of keyway where they just take like an end mill and then just mill out this keyway, and it winds up being round at both ends like this, right? Now, this is important to look at, that if we're using, annealed or quenched and drawn cold worked steels for our shaft material, that we've got pretty big KF, right? So KF of 1.3, 1.6, 1.3, 1.6, 2.0, right? So if we mill out a keyway and we use really hard steel, we're going to have a pretty significant fatigue stress concentration factor. And where is this thing? It's right under the gear, right? So that's where the stresses, the bending stresses are the highest. And then we have this huge bending stress concentration factor. 2, right? We're doubling our stress. Holy cow. So just be aware of that, that if you're going to use a keyway, if you're going to use a key, you got to have a keyway. If you're going to have a keyway, there's going to be a big stress concentration. Your shaft has to get bigger. That's just how it is. There's other ways to do this. If you, this might look familiar, if you've bought cheap stuff, cheap machinery or cheap stuff, there's oftentimes a split pin that's kind of flexible like this. Then so when you tap it into place, it kind of gets wedged in there. Here's a straight round pin, tapered round pin that only can go in one direction. And then here's a grooved pin. I've never actually seen one of these, but whatever, grooved pin. And typically they stay in there with some sort of interference fit. Right? It's sticky. There's enough friction that it won't fall out. It can't carry the same load that a key does, but it does also help keep things in place as far as their axial location. And if we were to look, no, I won't go back to that. Another way, right? Set screws, right? We've all seen set screws before. They come in different point. Most common is flat point, and then there's cone point or a cup point. I call these things cone points here. Number C is an oval point where it's kind of got a rounded edge. Typically, the way this would work is that we have some sort of a shaft that goes like that, but then we've got a flat. So there's a flat surface here. And so that's a flat there. And then I've got the hub, that goes something like this. And then the set screw would go down in there like that, right? And so if it's really pointy, like a cone point, right, it wedges into there deep like that. If you don't want to damage it, you use an oval point. Cone point gets pretty good grip, actually. And then the half dog versus a full dog, I don't know. That just gets a nice. I don't know. I think maybe you drill a hole in the flat, for the half dog to go in. I'm not exactly sure how these things work. The ones I'm most familiar with are the cone point and then the flat point. So let's see what they do. Yeah, we tap the hole in there. We have a flat milled onto the shaft. They might loosen up, right? So you don't want to use those really, unless you're willing to maintain them. One more thing, here's a pop quiz about set screws. So anywhere on the previous slide did it read, set screws are awesome for transmitting torque, all right? This is right here, I'll just give you guys a warning. This is the classic senior design uh, 351, 352 design approach. All right, please don't do that. Right, set screws are terrible for transmitting torque. Torque should be either a keyway or a spline, which we'll talk about next. Right, so don't use set screws for transmitting torque unless it's something that's really really low torque, like a needle gauge or something like that. Okay, last one as far as transmitting torque goes, splines. Yeah, this is getting a little long. Sorry. So there's so basically what it is. I guess I should show this picture here. So this is the gear spline, and then this is the shaft spline. You can see kind of this fits on this, right? And those slide together. They're fantastic. They can transmit lots of torque. They don't slip at all. They will probably never fail, but they cost a lot of money, right? They're very, very expensive to machine. Machining the spline on here, they're either broached or maybe they're forged like that. And these can be machined into place, but they're both really expensive. You'll find them in automotive transmissions a lot because they're expensive, but they have to run forever, right? But that's just so you know what splines are. Now we have to hold things in place axially, right? Shoulders, really, really strong, right? The problem with a shoulder, it really only works on one side. So if I have a shaft that looks like this, you know, and then my gear sits up on here like that. I don't know what that looks like, Bart Simpson's head. But the gear goes on here like this, right? The shoulder's awesome here, but I got to have something to do over here. What can I put over there, right? Well, how about a collar, right? A collar would be, so this is the shoulder here. Sound effects are important. And then we'd put a collar over here, right, which gets a little set screw or something to hold the collar in place. Right, that's one possible way to do it. And you know, and they can slide, right? It's not the most reliable way to do that. Retaining rings are good, right? What's a retaining ring? They're cheap, they're easy to use, very flexible assembly because I could have retaining rings on either side of anything, but they have huge stress concentrations. I'll show you a picture of that next. On the order of 5 in bending and 3 in torsion. So these are, you've probably seen these things here, retaining rings. They look something like this. You know, this looks like it might be an E retaining ring here, but this groove here, that little groove has got a huge KT, right? Huge stress concentrations. And again, if I'm using these 2 retaining rings to hold a gear in place, right, maximum bending is right here. So they're cheap, they're fast. They just go in and out with a pair of pliers, or this is actually not pliers, this is a special tool. That's a special tool. If you don't have the special tool, you wind up using a pair of needle nose pliers, and then you wind up slicing your hand open. That happens a lot, but they go in and out very easily, right? And they can go either it can, like, for instance, if you're trying to hold this bearing on the other side, there could be a retaining ring that goes out into the housing, or there could be one that goes into the shaft, right? The ones that go into the shaft obviously cause big time stress concentrations. All right, so where would the rings go? Here's where the retaining rings go, right? We've got a shoulder on this side, and then we've got a ring here, right? So there's a ring, and that goes in there, right? Unfortunately, it goes right where the gear is, so there's probably pretty high. Well, over here probably is the smaller one. So if this is in torsional equilibrium, this has got the bigger forces. So here's another ring right here, another ring there. Here's a ring holding the bearing in a pull. Look at these rings everywhere. So this is very common. Shoulder on one side, ring on the other. Pretty much the most common way you see these things put together. Certainly for the project. Most of you use retaining rings. What's the cost of this? Well, the cost is, I mean, stress concentration of 5, right? So you're going to have to make that shaft a lot bigger just to have that retaining ring there, right? A lot bigger. So like the cube root of 5, basically. Let's actually write that. Forces D to be the cubed root of 5 bigger. Right? Why is it cubed root of 5? I don't know. Kind of a fun quiz question. All right. So an example, I'm just going to talk through the example quick. Apparently we're making something delicious upstairs because the exhaust fan just kicked on. So I'm just going to talk through this quickly. We've got a diameter of 1 7/16 for the shaft. And it rotates at 600 revolutions per minute, transmits 40 horsepower. All right. Horribly inconvenient units. And then horsepower, come on, really? Inconvenient. All right. And then so through a gear, all right, select an appropriate key for the gear with a design factor of 1.5. Right, design factor of 1.5. Typically we want keys, so safety factor for key. I didn't type this in the notes, I just realized. Typically 1.1 to 1.5. So pretty low safety factor because you want that to fail first. They're cheap, right? You can just buy it from McMaster, buy it at the hardware store. They're cheap. But anyway, so what do we have to do here? We have to figure out our forces, which means we need to figure out our torque. Our torque is a combination of speed and power, right? So I know that torque equals, power equals torque times speed. These, of course, are really uncomfortable units. Once I have torque, I know my radius, which is a function of my diameter. Then I can figure out my force, and I can go back and get I can figure out how long this thing needs to be. Right? So first of all, from that table I showed you before, since I'm in, let's just go back quick. So since, oh no. All right, so my shaft falls somewhere in this range, right? It's in this range, so I'm going to use, or it must be in this range. I'm going to use a 3/8 inch square key, right? And so I've got another table for that, for metric keys. Yeah, 1 7/16, right? So I'd use a 3/8 key, right? And then I chose a cold drawn low carbon mild steed, generally available key stock, blah, 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 blah. Has a strength of 54 psi. Right? So, of course, this is some crazy formula. Horrible formula with units built in, which I want to avoid those. But we finally discovered that it's 4,200 pound-inches of torque, and that means that the force has to be 50 pounds, right? And so now if I go back and look at my 54 KSI, right, my yield shear strength will be 31.2 KSI, right? So I can get that. And so when I go through and do this, I figure out that, well, I'm going to use, this is the 3/8 of an inch, right, times the full length. So this is the shear, right? So this is for shear. And then I discovered that in order for this to work with the correct safety factor, so this is the safety factor here, I need the L to be 0.75. Okay. Now to resist crushing, I need to avoid just a normal stress failure. I just use the yield strength, right? Notice this is yield strength here, and this is shear strength here. I go through the same process, but it's only half the area, right? So there's an extra factor of 2 down in here. But I get to use I'm only using the full, I'm only using double rather than square root of 3, right? So this would be a longer one. So again, crushing is the critical mode of failure. All right. And I know I went through this really fast, but you can kind of see at least how it works. But again, I want to point out that crushing is the important thing. Okay, that's it. I will see you guys when I see you next.